Okay, so now we know that the Shor factorization of A takes the form u t u star for a unitary u and a triangular t. So if we multiply on the left by u star and on the right by u, we can rewrite this as u star A u is triangular. Now, to turn this into an algorithm, we first have to accept the fact that we have to kind of sneak up on this. There's no way to get the complete answer in a finite number of steps. So what I mean by that is, in the LU factorization, in the QR factorization, there's a well-defined finite sequence of steps. You generally work from top to bottom, left to right. When you reach the corner of the matrix, you're done. With eigenvalues, that's not possible, and there are deep theoretical reasons for that. It's known that we can't solve finding roots of general polynomials in finite amount of operations, and since there's a connection between roots of polynomials and eigenvalues of matrices, if you could solve the matrix eigenvalue problem, you could solve the polynomial root finding problem too, and since you can't do that, we know we can't do the eigenvalue problem either in a finite number of steps. So in principle, it's an iteration that never closes, never quite finishes, but in reality, you get so close to the answer in a reasonable amount of time that it doesn't act a whole lot differently from solving linear systems or solving linear least squares problems in practice. Okay, but in principle, what we have to do is to find not u all in one go, but u in a sequence of stages. Okay, so imagine it's a product of a bunch of unitary matrices, u1 to uk. Okay, and then its Hermitian would be the matrix that you see on the left of A here. And what we want is, in the limit, as k goes to infinity, we want this whole thing to look like T, an upper triangular matrix. Okay, so the way to think about this is to do it from the inside out. So if we just take the three innermost terms, right, we would call that A1. And then each of those has a U2 on the outside of that. So that becomes A2, right? So A2 has the U1 and the U2. But of course that's just U2 star times U2 with A1 in the middle, and so on. So we can do this by finding a sequence, A1, A2, A3, and so on, right? The idea being that the AKs converge to triangular. Now here's a bit of an odd-looking idea. So we're just going to be greedy and say, let's suppose we can do it in such a way that, and I have a misprint here. Okay, this should just be A here. Let's suppose we can just find a U1, right? So that U1 star A by itself is upper triangular. Okay, so that doesn't mean that A1 will be upper triangular, because A1, right? Oops. A1 has this extra term in it, right? The U1 on the right. So we know that after we multiply by U1, we can't expect it to be upper triangular, but we can try it anyway. And the nice thing about it is that we have a way of doing this, because what we're saying is that A is equal to U1 R1, and at least if we're thinking in the real case, this is just a QR factorization once again. And actually that's true for complex numbers too. So for the rest of the discussion, we may still keep using the complex notation, but everything's going to be real, so you might as well think of transposes. Okay, so we know how to do that. We know how to get our hands on the U1 matrix here. So what we'll do is, here's a matrix that we want to find the eigenvalues of. It's a van der Waals matrix. Well, we'll take the QR factorization of that matrix, right? So A is equal to Q1 R1. So that means R1 is equal to Q1 star A. So Q1 star A should be upper triangular. But then we multiply by Q1 again, and we get A1. Oops. And so A1 is not triangular. But we can keep going. So now we have A1. We take the QR factorization of A1. So A1 is Q2 R2. R2 is Q2 star A1. And A2 is Q2 star A1 Q2. Right? And we just keep going like this. Now, what you might notice about this, if we go back and compare to the original matrix, the numbers in the original matrix in this lower triangle were actually quite large initially. And then multiplying on the left by Q1 transpose made them 0, but then multiplying again made them not 0. But you'll notice that they're a lot smaller than when we started, by orders of magnitude. And then when we do it again, you can see, especially in the last row, if you look carefully at the last row, again, the numbers get smaller by a couple of orders of magnitude in some cases. And we do it again, we see they've gotten even smaller. And the ones above it are following behind. And so it seems like even though the matrices themselves don't stay triangular, they stay kind of close. And in fact, we can take this idea out further. So here are the actual eigenvalues of this matrix, lambda 1 to lambda 5. Just for reference. Then, so we're starting over with A. Now we're just going to do the QR factorization, and we're not going to number the A's. So, we start with A, we get A1, and then A1 becomes A2, and A2 becomes A3. Well, every time I'm just going to throw away the old A and keep the new one here. Okay, and what we see is after 20 iterations of this, that at least to this number of digits, most of those numbers in the lower triangle are 0. And if you compare the eigenvalues, okay, these diagonal numbers are looking an awful lot like the eigenvalues of the original matrix that we're looking for. And so this matrix is somehow close to T, triangular. There's one more twist in this process that makes it very sleek. So we've been saying that if we do a QR factorization of A, then that's the way of getting an upper triangular R, okay, by putting the Q transpose on the left. And then the matrix that we substitute for A is Q transpose A, Q. Well, that means that what we really have is Q, since Q transpose of A is R, that means we really have RQ. And so all we're really doing is saying, given A, take the QR factorization, and then reverse the order of the factors, and reassign that to A. It's really that simple. And this is called, this has various names. It's the QR algorithm, or the QR iteration, or it's named the Francis algorithm. It's kind of nice to have the algorithm named after the person who really discovered it. But you'll see it referred to all these different ways, not to be confused, right, with the term QR factorization. So QR factorization is an important step in the QR algorithm, but it's not the same thing. Okay, so here we see the QR iteration, the same one that we did before, the only thing that I changed was to go from Q prime AQ to just RQ. But the result is exactly the same because it's exactly the same mathematics. Okay, so let's do this with a little bit more experimental flair. So here again, we're starting over with the same matrix. Here are the exact eigenvalues again as lambda. Okay, we're going to do the QR iteration, and now what we're going to do is going to keep track of the errors. So if this is converging to a triangular matrix, then the eigenvalues of A should be along the diagonal. Okay, so what we'll do is we'll take those the numbers that are on the diagonal, and compare them to the actual eigenvalues. So we'll look at that difference as the error and see what happens. So if we plot the error as a function of the iteration number, okay, so k, and then this is lambda k minus akk, we see in fact they do decrease. It's hard to see how fast they decrease, but if we happen to use a log scale on the y-axis, we get this beautiful plot which reveals the very regular structure in the convergence. All right, so we'll talk more about this convergence rate and what it means.